Okay, very good. Back to our course. We were talking about instruction sets. Is that right? Any questions? We can move fast. We talked about what are instructions in a computer, a little about MIPS, and then started with just an example with arithmetic operations, which is add or subtract, something like that. And in there, I told you that usually in MIPS, we have 3 operands. First one is the destination in arithmetic operation. The next 2 are the operands, which will be, for example, added together, and the result would be stored in the destination. And we had an example of how a C code, for example, as a high-level language course, will be compiled to assembly. And then from assembly, it goes to machine code. And we talked about registers. There are 32 registers in MIPS. And we had an example. And I guess we were here at memory. So we talked about registers as a very handy memory locations, storage locations close to the processor. So processor has registers in hand for doing operations. But they are very small, only 32, for example, 32-bit register, 32 by 32-bit registers. And they are very small. If you want to write a program, you need much more of that than that. So we need main memory and structures, arrays, data. So many things will be stored in main memory, and they will be brought to the computer, to the registers. Then we work on them. Then we again put them back in the memory. And I told you that we call MIPS-like machine, which are RISC. They are load-store machines. It means that you do not have memory operations except load and store. You cannot add, for example, a number to a memory location. No, you cannot. If you want to add something to a memory location, you should bring it to the register file, then add, and then again back to the memory location. And we told you that it is byte addressable, and they are aligned as words, 32 bits. We talked about this, and then began the add. So I guess we were here last time. Any questions? Okay. So let's go to an example of memory operand, like what I've showed you for arithmetic operation. Here we have a memory operation. For example, this code. In C, we write G gets H plus A8, an array of a number of floating point numbers, or no, let's say here is the integer. They are words, long integers. Each one is 32-bit. It is an array of long integers. We want to add element 8 of that array, which is stored in memory, to H. And let's assume that G will be the destination and will be register S1. H will be, it is now in S2, so we would like to add register S2 to A8. A8 is a location of memory. The base address of that array, is now in S3. What are we doing? What are we saying? That when you want to refer to an array, you need the base address of the array, and then you have offset for each element. If it is an array, for example, if you want the 8th element of an array, so we have to go by offset 8 and find the element and bring it for whatever we want to do. So S1, S2, S3. S1 is G, S2 is H, and S3 is the base address of the array. How we are going to, how the compiler is compiling this code to assembly. Okay. The memory operand that we are using here is load. And load word. We are loading a word from memory, a 32-bit value, which will be A8. We will be talking about that from the memory. So the opcode, the command will be LW, load word from the memory. After LW, we will put the destination. We want to load from memory and put it where? So we want to put it, for example, somewhere, because we have to bring this value to the register file and then add it to it. So we put it to a temporary position. So this would be destination. And then the address of the memory that we would like to bring, to get the value from that and load it from there. The address of the memory consists of two things, a base and an offset. They are added together to make the address. The base would be an address. So the address is S3 here, and the offset would be a number. Here, which offset do we want? Which offset? Number? Which array element? 8. And 8 is the line. Each element is a line element. So if we've told you that it is byte addressable. So if the array has started from, let's say, this address, let's say, 1000, then each element of the array is 4 bytes because it is 32 bits. It is a long value. So each element of the array is 4 bytes. So the first element of the array would be stored in 1000, 1001, 1002, 1003. This would be the first element of the array, which would be, let's say, A0. Then we have A1. A1 starts from 1004. 4, 5, 6, 7. So the next 4 bytes would be the element number 1 of the array. This is element number 0, element number 1. Then element number 2 starts from 1000. How much? 1008. 1008, 1009, 1010, 1011 would be the element number 2 of array A, and so on. So if this is the case, if I want to find the array, the 8th element of array, what would be my offset? 8th element. What would be the offset? The first element was 0. The next element was 4. The next element would be 8. What would be the 8th element? Each element, how much byte each element needs? 4. So 8th element would be 32. The 32. Again, I am saying again. The offset 0, 1, 2, 3, these bytes would form the the number 0, the element number 0 of the array. Then byte number 4, 5, 6, 7, element number 1. 8, 9, 10, 11, element number 2, and so on. So element number 8, A8. Element number 8 has an offset of 32. Okay? Any questions? 32. So you should know where 32 came from. 32 is 4 times 8, and 8 is the array element number. So let's write the code right now. The code would be something like that. Index 8 requires offset of 32. So because 4 bytes per word we have, then we are loading to a temporary register like T0. Look at this. 32 is the offset, and S3 is the base address of the array here. Offset is 32, and base register is S3. So this instruction is saying that you go to the memory. Which address of memory? Address of base is S3, whatever it is. For example, in our case, it was 1000. Go to the memory from address 1000, offset 32 bytes, and then bring a word from that. If S3 is 1000, it means that go and bring 1032, 1033, 1034, 1035. Get the byte from these locations, make a word, and put this word in T0. Okay? And then, what did we do in our code, in our C code? Then we wanted to add this to H. H is in S2. So we will add them together, and the result should be stored in G. And G is S1. So we write add S1, which is the destination, S2, one of the sources, one of the operands, and T0. So they are added together, and the result will be put in S1. After doing these two instructions, the sum of H plus A8 is in G. Okay? Another example. So I've shown you up to now two kind of operations. Arithmetic operation, which had 3 operands, and all of the operands were registers. And then a load operation, which had an address. The address consists of offset and base, and a register. So the memory location is loaded and stored into the register. Okay. Another example. In this example, we are going also to, after calculating this, like the previous example, we are going to put the result back to the memory in memory location A12, in the 12th elements of the array. So we add H to 8th element, and the result will be stored in A12. Here, we are going to use a store because we are putting a register into the memory. The previous one will load something from the memory, and then here again we have to load from memory, then add it to H, and then the result will be put back to the memory. It means that it will be stored in memory, loaded, stored. And the command, the instruction would be SW, a store word. So we will see that. Before looking at that, I wrote to SW, and then what register do we want to store in memory? With the address. Address again has an offset. and a base. And the base is a register base. I will show you now. So here, let's assume that H is in S2, base address of A is S3, that's it. We have A and H because we get a 8 element and store it in 12 elements. So the code would be something like that. You see, first of all, we should load this. Pay attention. Load a store machine. Load a store machine means that you cannot add, you cannot operate on memory locations. You should bring it to the register, to the processor, and then whatever you want, apply, and then the result will be put back to the memory. Load and store. There is no operation. However, for example, in an x86, you have instructions that you can say, go and add this to the memory location that. With one instruction, you could add something to the memory location. And that's the reason that we call them CISC, complex instruction set, and here we call it RISC, reduced instruction set. So the first one is loading again from 32. The offset 8 element of this is 32, the index of 32, the location of 32 offset. So again, we bring it to T0. Then we have to add this. We have to add this to H, and let's store it in a temporary place. The temporary place that I've selected here is again T0. You add T0 to something, and then the result will be stored in T0. It's okay, because when you start this add, you have the value of T0 and S2. They added together. When the result is ready, it will be stored in T0. That's okay. You have seen that in high-level language also. For example, you write C gets C plus 2. So it means that the value of C is added. The current value of C is added to 2, and the result will be stored in C. This is something like that at T0 and S2 and T0. Okay. The next, now we have calculated the sum. Now we have to store it in memory. Which memory? 12, number 12. Element number 12. What would be the offset of number 12? 48. 12 times 4. 48. Because each element has 4 bytes. So the element number 12 starts from byte number offset 48, byte offset of 48. So now we load from offset 48, base is S3, so we load, store. So we want to store the value of T0 to this location. As you see, the syntax is like that. SW, store word, the register that we want to store in the memory, and then the memory address. Okay, this is another example. As you have seen here, we are using registers and memory. And with memory, we have lots of storage and arrays, data, everything will be stored in memory because we don't have a space in register. Register is a very small amount of storage. Registers are much faster because they are close to the processor and they are not in memory. Processor, if you remember, we had 4 or 5 elements. Processor, input, output, memory in a processor. And processor itself had control pass and data pass. We talked about that before, yeah? Okay. So processor is something, memory is something else, input, output is also something else. The processor, whatever is inside the processor, they are accessible from the processor and they are fast. We can work with them very easily. But the other things are outside the processor. If we want to find anything in memory, processor should get access to memory and get something from the memory, bring it to the processor. So registers are much faster than memory. And that's why we are doing our operations on registers. Operating on memory requires load and stores, nothing else. No instruction exists for accessing memory locations, contrary to maybe some other CPUs. They might have access to memory with other operations. But here in MIPS, no memory access except load and store. Load gets from memory, store puts in the memory. And therefore, we might need more execution. In x86, you could write one instruction and you get something from memory, add to something and put back to the memory in one instruction. Here, you should make it 3 instructions, as we saw in the previous example. Bring from memory, add, and then put it back to the memory with 3 instructions. So the instructions are more in risk, but they are much faster. We will talk about that later. And compilers should use registers. If that's the limitation, that's the constraints of the compiler. Compiler has only these registers. Whenever it wants to access to memory, it should bring it to the registers and do whatever it wants. Only a spill to memory for less frequency used operation. If compiler should be smart, or even you as the programmer should be smart to bring something to registers that you are using them lots of time. If there is something that you don't need it in your program for a long time, it's good to put it back into the memory. And whenever we want it in our program, so bring it again to the registers. So it is up to the programmer and compilers. Compilers are smart. They are trying to see which locations, which data we are working on that. The compiler brings the data into the registers and works on them. And whatever there is no need, it will be put back to the memory. And the registers, they are in the processor, they are fast, they are small set, so we can design a very optimized design circuit for these registers. And this is one of the basic rules that we told you, that the smaller is faster, smaller is better. I've told you there are 4 rules for designing. I will bring it later for you again. So one operation was add, one operation was load, one was store. Now we go to another kind of operations, which we call them immediate operations. What does immediate mean? Does anybody know? Immediate operands. Immediate operands. Yes?
Like an operand you can use without having to call it from memory?
Yes.
More register?
But how come? You don't need memory? Yeah, that was correct. In immediate operands, we don't need to go to memory, either for loading or storing. So what is that? It is some kind of constant operands. For example, you want to add number 4 to register S0. S0, you want to add 4 to that. 4 is a number, it's a constant. It is not something in the memory. And you, as a programmer, you want to add 4. So you write 4. In C, you write C, for example, C or any variable, C plus 4. 4 is a constant. a number, and this is an immediate operand in assembly. Constant data which will be specified in the instruction. When we write instruction, it is there. It is there. C gets C plus 4. The same thing we will have in assembly. For example, the opcode would be add I means add immediate. Add immediate. Destination again, a register which is destination, source, and the immediate value which should be added to that. Here exactly, we are doing something like C gets C plus 4. So we add 4 to the register S3, and the result will be stored in S3. This is immediate operand, compared to the previous one, which was a memory operand. We loaded from the memory first, and then, for example, add. Here you see there is only add operation. In arithmetic operations, we had add and sub. But here, we don't have sub I. Why? Why don't we have sub I? Can anybody say? Your guess, whatever it is. It shouldn't be correct, yes.
Add a negative number and it would do the same thing.
Perfect. So, but again, why don't we use sub I? You were right completely.
It's less like command is better.
Why it's better?
It's simpler and
Exactly, perfect. Simpler. Simplicity makes a better design. Our design would be less complex. And when our design is less complex, it means that it is faster. It is more optimized. It needs less. It consumes less power. It will be faster and will be executed in less time. So no subtracting. That's the only reason. They thought about it. They said, okay, we have negative numbers, so we can use add with negative numbers. And then why do we need another subtract sub immediate? You could say the same thing for the add and sub operations. Why did we have sub over there? Who could answer? We had sub there, but we don't have sub I here. Here, the answer is this. Just use the negative constant. It's exactly right. But why didn't we say the same thing in the sub add and sub command that we had before? It's all design. The designer should think how many times in a program we need sub immediate, or we need add and we need sub. So it will look at, for example, benchmarks. There was slides about benchmark in our previous slides that we haven't talked about in the class. So either you should read it from the book, or I will give you a recorded video so you could use it. So the designer should look at the programs. How many times do we need to add subtract? How many times do we need to add to do add? How many times do we need sub I? How many times do we need add I? And based on the numbers, it calculates the cost and the performance. So if you implement sub I, how much performance will be improved with the cost? Because it has costs. When you add an instruction to the machine, then the controller would be more complex. It has costs. But how much improvement in performance do we have? And so they evaluate all of these things, and they reach to a point for a good cost performance comprises. So here, for example, this point is good. We don't need sub I, but we need sub. And that's all the design thinking. For example, this one is subtracting 1 from S1 and putting the result to S2. S1 added to -1. We will talk about minus numbers. You know, I guess you have seen that the minus numbers, negative numbers in ITI 1100. So again, you see, we use the common case more. Whichever is using more. Add is add immediate, we need that. Sub immediate, we need less. So we make the common case faster. We make an instruction for this more common instruction, and we make it fast. But for the sub I, we just use negative. And the next things, I will tell you later that these operands, an immediate operand, is only 16-bit, not a 32-bit value. We are doing operations in 32-bit operations in MIPS. We have a 32-bit machine. But immediate values, these operands, are 16 bits. Why? Who could say why? In addition to this, the common case is a smaller constant. You don't want to add, for example, 1 billion to something. You usually add 1, 2, 3, 4 for your loops, for your offset. In your program, you add for C, it gets C plus 4. You don't write C gets C plus 1 billion in your program. I don't think so. But you use smaller constants, and it's common, so we think of this. What else could you say? Okay, the small constants are common, but why don't we put, let's say, 24 bits here? Why 16 bits? It's hard to guess for the time being, and it is another design rule that we make regularity as much as we can. And one of the basic regularities in MIPS instruction set is that all of the instructions have the same size, and they all have 32 bits. It's very important. Every instruction, this instruction, load instruction, add instruction, subtract, whatever instruction we will show you, they all have fixed length of 32 bits. So if the whole instruction is 32 bits, then we need to put the opcode in the instruction, we need to put the operands in the instructions, then only 16-bit is left for the immediate value. And they have chosen to use 16-bit limit for immediate value. Okay, so I am telling you something which we will see later in our course. And they are good. Immediate values, they are in the instructions. So whenever you get the instructions, you fetch it, then the value is there. You don't need again to go to the memory and bring the value like the previous example that we had. Before going further, let me say another thing. It's true that immediate operand avoids a load instructions, but each instruction should be fetched from memory. Have you heard fetch before? No? Okay. So we should talk about it. We should talk about it. Because instructions are in memory. Whenever processor starts doing something, executing, it should bring the instructions from the memory and then execute. So there is access to memory to bring the instruction and then executing. But here we are saying there is no need of another load instruction, another access to memory. The first access, which was for getting the instruction, which will be the same for this. This is also an instruction, and it is stored in memory. It should become from memory, and then the execution starts on this instruction. So these are the same. So for all the instructions, when we have an immediate value, then there is no need for a load. Just the number is there and we do the operation. Yes.
So in this example here, is it fetching a word from the memory and then just adding a constant with add immediate?
Fetching an instruction from memory, which is 32 bits. And I will show you now in our lecture how this will be decoded, will be encoded as 32 bits. So fetching a 32 bit, then processors look at this 32-bit number. It says, okay, here it is an add I. So it understands that this instruction is add I. So then after it finds that it is add I from, for example, 5 bits of the 32 bits, then looks for the source register, looks for the source. Then looks for the target, the target register. Then looks for the source register, and then goes and brings the 16-bit immediate value, and they will be added together. Okay. So this is something that we are going to talk today, hopefully, if we have time. Yes. Another MIPS design is a constant zero, because usually you will use zero in your programs, and you need that. So MIPS put a specific register, called it register 0, and it is always 0. You cannot change it. You cannot load something to that register or change it or add something to that. It is always 0, and it will help for your writing your program. For example, you want to move 2 registers. Whatever value is now in S1, put it in S2. How could we do that? In another machine, for example, x86, there is a register command called move. So you get a register and then you move it to this register. Again, RISC rule is to make the common case fast and make regularity and make an reduced instruction set. So in MIPS, we don't have move. So how could we do that? We want to move a register from one register to another register. This is very common. For example, you have a register, you want to store it somewhere as a place, and then do something on this register, and then bring it back, and so on. So many things you would like to do. So you need to move between registers. So what we do, we use add. For example, here, S1 plus 0, the result will be stored in T2. It means what? It means moving S1 to T2. Okay, something like that in other machines would be move T2 and S1. But here we don't have move instruction. We have add instruction, and we will use add plus the 0 register to make a move. Yes?
Why can we not use the add I command?
Immediate.
Why can we not use like just put 0 for the?
No, 0 is a register, so it is not an immediate. You could use 0 for that, and then yes, you could have used add I S1 or T1 like this one, S1 and 0. Yes, you could do that. The same thing. I guess I should see. That would be faster. Not faster, it means of the number of clock cycles. We will think about it later. But yes, this is correct also. You could use an immediate 0 value for that. As you saw in ITI 1100, we have unsigned and signed operations, signed arithmetic. Unsigned is just using the numbers as they are. For example, an n-bit number in a binary n-bit number will be converted to decimal with this equation. First bit multiplied by 2 to the 0, the next one 2 to the 1, 2 to the 2, and they are added together, something like that. first bit, next bit, and so on. So this is the binary conversion. You have done that before, yeah? No need to do it again, yeah? This number, or let's say this. What would be the decimal equivalent of that? 0 times 2 to the 0, which is 0. 1 times 2 is 2. 1 times 2 to the 2 is 4. 1 times 2 to the 3 is 8. 0 times 2 to the 4 is 0. 1 to the 5 is 32. And 1 times 2 to the 6 is 64. So the value would be 64 plus 32, 96 plus 8 is 104, 108, 110. This binary value would be 110 in decimal. Okay, this was how we converted a binary value to a decimal value. You had seen that in your previous courses. And you could do the successive divisions to convert from decimal to the binary. I don't go through that now. And the range is from 0 to 2 to the n minus 1. For example, here I have 1, 2, 3, 4, 5, 6, 7 bits number. So the range would be from 0 to 2 to the 7 is 128 minus 1, 2 to 127. So the range of this number is from 0 to 127. Yeah? You have seen that before. If you are not very good at these operations, you do practice again. You need to be master on these binary numbers. Example. For example, this is a 32-bit binary number. Oh, it's a big number, but it has only these ones. So if you look at that, this would be 1 plus 2, 3 plus 8 is 11. So it is 11. The rest are 0. 32-bit number. And if you use 32-bit, then the range would be from 0 to 4,294 billion and 967 times, whatever it is. It is 2 to the 32 minus 1. This value is 2 to the 32 minus. But we have another system which we call it two's complement. The two's complement systems tries to make negative numbers in binary. The first thing that we have to say about two's complement, that is 1 bit of a number. So if we have, for example, 8-bit numbers, 8 bits, the most significant bit, the leftmost bit, is the sign. If it is 1, means that this is a negative number, and if this is 0, it means that it is a positive number. So the first thing is that. How do we calculate two's complement? I will give you the equation first, but we will work on that more. The equation would be this. You multiply this by 2 to the 0. The next one, 2 to the 1. The next one, 2 to the 2, like whatever we have done in unsigned. 2 to the 3, 4, 5, 6. And this one will be multiplied by minus 2 to the 7. So the difference is that. And with this, you calculate the number. Let's do 2 examples. For example, I put 0 at the sign, which again will be the same as what we have told before. 0, let's say 1, 1, 0, 0, 1, 1, 0. This is an 8-bit number, and we know that it would be a positive number, and the value in decimal would be 2, 4, 6, 16, 32, 38. plus 64. 38 plus 64. How much would it be? 38 plus 64 is 102, if I am not mistaken. 102 decimal. This is the value of this equivalent decimal value of this. Now let's put, instead of that, we calculate this. 1100110. How much is this? What is the equivalent of this in two's complement system? Again, I am saying that two's complement system. Yeah?
Negative 102?
No. Let's calculate. Yeah, it is not negative 102. It's the point is that we have to calculate. So up to here we have calculated. It was 102. Yes? And this one is minus 2 to the 7, which is 128. So then we have minus 1 to 28. So this number is, let me write it so I could do that. 2, 6, 0 up to 2, 0. So this one is minus 26. This number is minus 26. Okay? Minus 26. The equation is that, but we can do something which might be simpler. I don't know. You decide which one do you want to do. The other thing is that converting a negative to positive or vice versa, we can do this. We can invert, complement each bit and then add 1 to it. Okay? Complement each bit and then add 1 to it. So let's do that. Let's do this. Here was our number. So complement each bit. 0 gets 1. 1, 0. 1, 0. 0, 0, 1, 1. 1, 1 is 0. 0, 1 is 0. So this is the complement of every bit. And then we have to add 1 to that. 1 plus 1 is 0 with 1 here. 1 plus 0 is 1, 0, 1, 1, 0, 0, 0. So the number is this. This is the negative of that number. What is this? 2, 8, 10 plus 16 is 26. Again, 26. You see, that number was minus 26. When I 2's complemented, it was plus 26. Minus 26 plus 26. Another thing that you could do, I say you need practice. Another thing you could do is, let me write here because it has more. Here, what was our number? It was 111. 0, 0, 1, 1, 0, 0, 1. No, it is too much. 1, 2, 3, 4, 5, 6, 7, 8. What is our number? Something okay, I guess these two were 8-bit. This was our number, which we calculated, and it was minus 26. I hope that I write it correctly. How do you 2's complement it? Another way is this. So the first one I told you, you complement every bit and then add 1 to that. Another way is you start from the right and go up to the first one. And from that, you complement everything. So the first bit is 0, I will keep it. The next one is 1. So this is my first one. From this position, I will complement everything. So the next one is 1, which is 0, 1, 1, 0, 0, 0. This will be the 2's complement of that. If you look at this again, this is 26. So you could do whatever you want. They are just playing with numbers. 2's complement system. And the beauty of this system is that when you subtract two numbers, A minus B, you could do A plus 2's complement of B. 2's complement. This is very good. And this is the system, how the system is made. You have negative numbers, you can add, and so on. Okay. So 2's complement, an 8-bit number, you calculate it like that. The difference is this one, which is minus. The most significant bit is minus, so it will be multiplied by 2 to the minus 2 to the n minus 1. And the range would be what? If we have 8-bit number, if it is unsigned, the range is from 0 to 255. If it is signed 2's complement, the range would be, who could say? The positive, it is a 7-bit positive number, which will be 127. But the negative would be, the range would be minus 128 to up to 127. So for 32 bits, I don't know, here is that. For 32 bits is this. This is the minus, the most negative value with 32 bits, and this is the largest positive value. And this is another example. What was that? Okay, it is the number, and wanted to calculate what would be this as a negative number. The negative number was minus 4. Calculated like that. Again, I told you, instead of doing all of these too many multiplications and too many to the power, you could just complement it and then add 1. If you complement it, all of them is 0, this one is 1, 1, and then you add 1 to that. 1 plus 1, 1 is 1, 0, 0, which is 4. So it is minus 4. Bit 31 is signed, so 1, if it is 1, it means negative. If it is 0, it means positive. Minus 2 to the n minus 1 is a positive number, and we don't have it with the n-bit number. The n-bit 8-bit number goes maximum to 127. It doesn't go to 128. This would be 128 in 8-bit numbers. But we have minus 128. Non-negative numbers, they are the same as the unsigned as we have typed before, but the negative numbers are different. And this is good if you look at this. This is 0. Of course, this is 0. This is minus 1. If you have all 1, then it is minus 1. Here, pay attention. If you are talking about 2's complement in 8-bit system, then minus 1 would be this. If you want to write minus 1 in 16-bit system, what would be the minus 1? The mistake that you might do is that, okay, you say this is minus 1 in 8-bit, so I will put 0 here, and this is minus 1 in 16-bit, which is not correct. The minus 1 in 16-bit system is this. Got it? Minus 1 is this. So this is a rule, this is a thing that you should consider. When you want to extend something to more bits, you should sign extend it, not just putting 0. Up to now, you say, okay, this is my 4-bit number, I want to make it 8-bit, so I put 0 here. No, this is okay for unsigned values. But for signed values, for 2's complement system, you should sign extend it. If this is your number in 8 bits, then you want to make it 16 bits, you should extend the sign the leftmost bit should be extended. Whatever you want, 16 bit, 32 bits, whatever bit you want, you should sign extend it. So this is -1, and it is very obvious. You complement it, it becomes 0, and then add 1 to it, it becomes 1. So it is -1. And this is the most negative number, which has a 1 and all the 0. And this is the largest positive number, a 0, and all the rest is 1. Okay? Makes sense, yeah? Okay, I told you. When you want to do a negation in two's complement system, complement and then 1 and then add to 1. If this is the case, so if x bar, let's say the negative of x in two's complement is, x bar is the complement of that. If the negative of x bar plus x bar plus 1 is minus x. If you want to find minus x, you should complement it and then plus add 1 to it. So this is the equation. Minus x is complement of x plus 1. So if you bring x to this position, x bar plus x becomes -1. Yeah, this is the one. X plus x bar is -1. Negate 2. If you want to negate 2, you write 2 first, and then complement everything, and then add 1 to it. This is the one. Or, as I told you, you start from the right until the first one, and then you complement everything. Start from the right, so we have 0 and then 1. We've reached the first one. From this point, you invert everything, so everything will be 1. So this is -2. And I told you about the sign extension. If you want to extend it to a larger number of bits, you have to sign extend it. Otherwise, you are changing the sign, and it will be very bad. In MIPS, I told you, for example, add I gets a register as the source, and then another register as the destination, another register as the source, and immediate value. And the immediate value was how many bits? 16. Told you. It is 16 bits in the instruction. So this is 16 bits, but they are 32 bits, the registers. So we have to extend it. We do it, we sign extend it. If the immediate is negative, then 1 is added to the left. If it is positive, then 0 will be added and extended. The same thing for load by, load high, which we will see later, because again they have something, they bringing something which is less than 32 bits. And then we want to make operations with a 32-bit number, so we have to extend it. And also branch, we will talk about it, that the branch address has a displacement of less than 32 bits. And so we have to extend it. We replicate the sign bit to the left. If it is positive, 0. If it is negative, 1. Unsigned values extend with 0. Signed values extend with 1. For example, this is -2 in 8-bit. If you want to make it 16-bit, it becomes like that. Okay, so let's go to quiz now, and then come back again here. I would like to also to talk a little about projects. If anybody is interested in doing project as a bonus thing, as a voluntary, then we will talk about the project also. So let's stop here. Do I? No, let's record. Okay, let's go to quiz. Before that, let's see what did we have in reflections. What did we have in reflections? What did we have? Reflection. Two reflections, alignment and endian. Okay, let's see, what did you write? Okay, the first answer is with Vince. Is Vince here? Vince? No? So we go to next. Kevin? No? Yeah, Kevin. Okay. What did you write about alignment? So the question was, which of these two tasks work in MIPS? Explain your answer. So Kevin saying that both of the tasks can work in MIPS. We can use LUI, unsigned load immediate instruction, to load you. So you were very front to load the upper immediate value into register, then the ORI, or immediate, instruction performs a bitwise OR with the lower immediate value. Lastly, the store value instruction stores the results in the specified. Oh, Kevin, you are very far in front of me. Yeah, are you here, Kevin? Okay. Then register 0 is used as an absolute address. Oh, very good. So he knows everything. How do you know these things? Okay. But your answer is not correct.
Okay.
Why? Who could say? Maybe we could go to the next answer. Yes.
For the first one, it's not divisible by 4, right?
Yes. Exactly. So the who are you?
Arnav.
Ardolph?
It's ARNAV.
ARNV. Okay.
Yeah, it posted like at the very end though.
Okay. So the next one is Choi. Isabel. Yeah, is she here? No? Why? Why do we have so many absent? So again, she wrote both of these two task works, which is not correct. MIPS. The next one, Rachel. MIPS, Rachel, yeah. MIPS without intellectual is a type of risk. Okay, which one is working? Based on the given direction, only the first task. So you are right. Why? Because the second task, let's see the first task. The first task is doing. Oh, you are wrong also. The first one is 6. The second one is C. 6 is not divisible by 4. So it is not aligned. The question was alignment. It is, as you could guess from the title, it is for alignment. And for alignment, I've told you that when you want to store a word into the memory, it should be aligned and at the correct position, which should be divided by 4. So the correct answer is that this one is not working because it is not aligned, but the other one is working. The other one, which is C. C is 12. 12 is a multiplication of 4, so it works.
I mean, the first one can work. It just wouldn't be efficient because you can.
No, cannot work. In something like x86, it works, but it is not efficient. In something like MIPS, it cannot work. It will give you exception, error. Say, I cannot do this.
Can you not like split it up and store it?
You could do it yourself. Yeah, you could make it into half-word, for example, store. Yes, you could. But this...
So you can store that value at that memory address.
Oh, okay. Yeah, maybe I had to write it in one access.
So you have to say in one access.
In one access. So yeah, you are right. If somebody like Kevin was doing something like that, I guess maybe he's doing it in two separate accesses. Yeah, you are right. You are right. I had to write it in one access. Yeah. What was your name?
McQueen?
McQueen.
Yeah.
McQueen was right. You could do it if you need to do something like that. Your hand is not tied. You could do it, but it is not in one axis. You make it two axis. Half word will be stored in location 6, and the next half word will be stored in location 8. 6 and 8. They are not aligned. 6 and 8 are not aligned. But you can do it, but not in one axis. You are completely right. I have to make it one axis like next time. Very good. Perfect. So the next one was endian. In the previous question, two tasks are presented. For those of them which are correct, which I meant by one axis, I could say for both of them, you could write that. Tell me how memory is stored. So let's see, Vince. Vince was not here, no? Yeah, Vince. What Kevin was here, we go past. Isabel, we read. Okay. Akachukwa. Yes. Okay. So what did you write? To store the hex number this, to memory location this, we can use, so what we can use, that's right. We first, so you are off, France, so why do I teach you? You know everything. We first load the value this into the, my question is not this. My question is how it is stored in memory based on big endian thing. You could guess that from the title, endian. Obtain the God. Finally, we store the value in register tomorrow. Nah. So where is that? Simultaneous with the, no, you are explaining how are you going to do that. So your answer is almost the answer to the previous question, not to this question. Let's see, Rachel. We saw Rachel before, so let's go to Christian. Christian,
Mine's not right.
Okay.
I'm assuming with the big endian method, you would just have to read the input from the highest order to the highest order bit to the lowest order.
So that's right.
And then store it from high order memory to low.
Oh no, store from the lower. Yeah.
Oh,
so
low to high?
High goes to low, low goes to high. The big endian is that. With little endian, low goes to low, high goes to low, high goes to high. So let's see what you have. Christian wrote. So 45 to F something can be stored to in, and the hex number in can be stored to this allocated memory in order to, big endian, the endian process hex value bit, but you haven't, here. Hexadecimal value to this. The hex number is broken into bits of 2 and is assigned to the low level memory. Hex value 45, this is what I am looking for. Hex value 45 are assigned to memory location 6, which is correct. Hex value 45 goes to 6. Hex value 2F goes to where? 2F?
7. I said 7.
7, that's right. So the highest goes to lowest. 45 goes to 6, 2F goes to 7, 3D goes to 8, and 8A goes to 9. So you were right. Okay, perfect. So let's do the quiz and then talk about the projects. We have time. Quiz. Where is quiz? Because the time has passed, I have to change the time. So, I guess it was 9 minutes. So we will put an end on 9:50. Oh, it is very bad. Then how could we talk about the projects? So let's do the quiz next time. And now talk a little bit about the projects. Yeah, it's better because you want to start your work on the project. So we will do the quiz next time. The projects. The project, you could find the PowerPoint in project module content. project module here. So this is my ideas. These are just suggestions. If you find any other projects related to our course, it is okay. You just tell me, and then I approve, and then you could start working on the project. Otherwise, you could use one of these projects. So I download it, open the file, and then coming here. So they are just, again, I am saying that they are suggestion. So the description, in our description, we wanted to do a digital computer design, register transfer, and micro operations. These were our course objectives. So any project who could help you for these objectives, it would be acceptable. So it's not limited to what I am now presenting. Whatever you want, but it should be that. And you know that for project we had put 20% extra mark. So if you do it well, then you get 20. If you don't, then you get less, and we will evaluate. So some project ideas. First one, instruction set architecture. You design an instruction set architecture, like what I am showing you about the MIPS. And I put you some subtasks for each project. You design a single cycle processor. A processor which is single cycle. It is not pipeline, it is not multi-cycle. We will talk about these in our courses. But if you want to start your project, you could start. You could even go yourself and find out how to do that. Or you would be very consider about these things. If I am lecturing, then I am telling about single cycle processor, then you would use it in your project. Another thing is a pipeline processor. You design a pipeline processor. We will do it in our course for MIPS, but I want you to do it for something else, for your own processor, very simpler processor with limited instructions, and what it should be, for example, pipeline. The other one is performance analysis module. So you have a processor, you want to see how it performs with different benchmarks, with different operations, how calculate the CPI, clock per instructions, we talked about it before, and so on. So you could, whenever you liked it, you could go through the subtasks that I've put here and see if you are okay with that, and then we start defining the project. For defining a project, you need the title, you need the deliverables, and you need the specifications of what you are going to build. Pipeline visualization. When we have a processor, I told you, we fetch the RAM memory, decode the instruction, and then execute it. And when it is pipeline, it goes to a pipe to be executed one by one. This project is saying that I want you to visualize that. This instruction now in fetch stage, the other instruction is now in decode stage, the other instruction is now in execution stage, and so on. Some kind of visualization. The next one is branch prediction. Since we are using a pipeline processor, then we are fetching, the other instruction is decoded, the other instruction, the previous instruction, is executed. When we have a branch instruction, branch means that it depends on a condition. If a condition is true, then the code jumps to somewhere. If not, it goes to somewhere else. So we don't know the result of the condition. It should be calculated later in decoding stage or executing stage. Before that, we don't know the next instruction. So the next instruction which we need to be fetched from the memory, we don't know. And then we do branch prediction. We don't know the exact result of the branch, we predict. I've told you a lot in future what we are going to talk about in future, but I just want to give you an idea because you don't know these things. To have an idea, you select it. If you liked it, then you will learn about that. So branch prediction module. Exception handling. Again, in a pipeline processor, exception handling is hard. Data forwarding. Again, if we have dependency between two instructions, this instruction is adding two things, and the next instruction is using the result, the sum of the previous one. If we have a pipeline processor, it has not been completed in the execution state, but the next one is started. So where is the result? It should wait. But we could do some kind of forwarding. I just give you ideas so you see what is forwarding and what happens in the processor. If you liked it, go and design. Cache-friendly instruction scheduling. So we have cache. Cache is that a temporary memory close to the processor, which is faster. I told you it is a static RAM compared to dynamic RAM for the main memory. So you bring something to the static RAM. If you write a program that uses this amount of less memory compared to main memory, that would be better. You write a program which will use a better usage of the memory. So this is cache-friendly instruction scheduling. Next, branch delay slot. I guess it has, okay, 1 minute we have. In branch prediction, I told you, the other solution is to have a branch delay slot. You Google anything or you read the book, you just go to the book and look for that. If you liked it, then select the project. Branch prediction analysis. Exception, it's some kind of repeated, but it's a little bit different than the previous one. Go to the subtasks. Instruction fetch optimization. You fetch instruction and then execute. How could we make it better in especially a pipeline processor? Data dependency. I talked about data forwarding. Here we are doing data dependency analysis and memory hierarchy cache performance analysis. Advanced instructions. So we design instruction set for MIPS. Then you want to add an instruction to that. How could you do that? This is a project that you add an instruction to instruction set of MIPS. Dynamic instruction set execution, which will some kind of guessing and doing faster, out of order execution. Floating point unit. We talked in our course about integer module, just operation add, subtract, these things. But about floating point, adding two floating point number, this would be a good project. Multiplier. Again, we are in our course, I don't think we have time to go to multiplier. So anybody could do a multiplier as a project and just putting everything in a system, in an FPGA, like a system on chip, processor, interface, and everything in a system and designing a system. So these were ideas. I am not saying that you should only work on this, but I gave you some ideas. So either you select one of these or you bring your own idea and I will approve. But it needs my approval. Don't forget that you give me your idea, we will talk, and after approval, you could work on your project. Any questions? Yes.
Are you projects or group projects?
Groups. Yeah, groups is better. 2 or 3 people. Okay, true. Yes.
Quizzes tomorrow.
Quiz?
Because there's class.
Yes. Yeah, 2 quizzes for the next session. Today is Friday, so the next session is Monday. So Monday we will have 2 quizzes.
Class is tomorrow. Are we doing our Monday tomorrow or?
Tomorrow we have class. No, it is tutorial class. No quiz and tutorial. Just the tutorial.
So are you holding a lecture tomorrow?
No.
Okay, because
Tutorial, yeah.
Victoria Day, the school wanted us to follow the Monday schedule tomorrow.
Oh, yeah. I didn't realize it. Okay, so if it is, so when is the time? The same schedule as Monday?
Yeah, Monday.
So we should have a class on 2:30.
Only if you want to hold the lecture.
Yeah. If you never, if I don't do it, the university might fire me. Yeah, or no? I don't know.
Yeah, so it would be tomorrow at 2:30, and there's
What's your vote?
Monday.
Monday, of course. You are similar to me. For me, it's Monday. Yeah. So let's see each other on Monday. No tomorrow. No.
TGD tomorrow, or no TGD?
I don't know. You should ask the TA. Okay. Questions?